I'm going to come back to the glass fibres now. I talked about this at the beginning. Glass fibres have a huge impact on not just the mechanical properties, but also the electrical properties of the material. Glass fibres are formed in a big furnace by melting a composition of material, composition of glass, and we end up producing fibres from this. So there are fibres wound on here, and these are the standard fibres that are used. There aren't many others, by the way. This bushing you see on there is a very expensive piece of material. They don't change it very much. So when they have a bushing, they keep it and they produce these materials only. And there's a designation for these, E electrical grade, C continuous filament, and then the fibre diameter. They range between 5 microns and 9 microns, so they're pretty thin. A human hair is around 100 microns. Mine is somewhat less now, to be honest, but you can see the range. And then we group these together between 200 and 400 filaments per strand. So that's the fibre that we end up with. I didn't bring any glass fibres in, but I brought some aramid fibres. Aramid is what bulletproof clothing is made from. So I'll pass that around so you can have an idea what it looks like. I try to tidy it up, but you can't even cut it. It's so strong. There's no way of actually chopping the material. But that is strands of several hundred fibres of aramid materials. And that's what the glass would look like as well. So from those, then the product is woven. So we take lots of ends of these. We run these around 3 kilometres long, all together, as you see in the bottom one there. And then we shoot another fibre across the other way, just like we weave clothing, just the same technology exactly. And that's a picture of a plain fabric weave, so one over, one under. And there are different names for this. The names don't really matter. The names are on the left, where we say style. There's a weight, and there's various other properties in there. And the tex value, which is quite interesting. The tex is the 68, the 22, and so on. The tex means how many grams per kilometre. That's what that unit measures. And we end up with these standard materials, standard yarns. And we can then build the glass fabrics. And the glass fabrics look a bit like this. That's a big lump of glass fabric, so you get an idea what it looks like. And I have other samples of smaller ones, or thinner ones. I'll pass that around here so you can see different kinds of glass fabric in there, just different thicknesses. And it's from those that we build. These are our basic building blocks. We build all our materials from these glass fabrics. And here's some pictures of them. So I started with fairly thick ones, and I'm going to work down towards thinner ones, and you'll see the problem as we go forward. So the 7628 glass fabric is 200 grams per square metre. 2116 is 104, 213 78. As you see, you're seeing a bit more air as we're moving on here. Because of the construction of these materials, we end up with a less dense material, less dense fabric. If I move even further to thinner materials, I go to 225, 1080, 106. 106 is one of the thinnest materials you can buy. You can go down to 104, 102 even, 101. So there are thinner ones, but it's probably the thinnest commercially available, widely commercially available material. And you see there's a lot of gaps in there now as we move forward. So that in itself is not a big issue in terms of the overall performance of the material. But if you think about dielectric constant, glass has a decay of around 6.6. These are all 1 megahertz, by the way, although they don't change too much. Resin has a decay of around 3.5. So it's around 2 to 1-ish. It's that kind of number. FR4 has a value you can calculate from the proportions of these two materials. So a very simple equation. And you end up with a chart like this. So how much resin you've got in there, you can see the dielectric constant at different frequencies. Very, very simple. But of course, that's a macro property. That's the property of the entire substrate over a large area. And that's really where the problem arises. We're not working at those kind of scales anymore. We're not working over inches or tens of inches. We're working over very, very small areas. And this is an example. Apologies, Dan. I've put up a differential pair here that I know doesn't exist. But anyway, here is one. And you see the track A, and there's a reference plane underneath it. A is basically, between there and the reference plane, is mainly glass. These little fibres you see running across, and that's the bundle of fibres you see coming towards you. And the decay of that bundle is around about 6 something. So that gap between that track and that reference plane is around 6 point something, more or less. Maybe it's 6. The other trace, B trace, has got very little glass in between, just the way the tracks have fallen. They've fallen into a resin-rich or a glass-rich area. So there, it's mainly resin. So decay is around 3.5. The problem arising there is the speed of transmission. The speed of transmission is relative to the speed of light, and it varies to the inverse of the square root of the decay. So if you reduce the decay, you get a higher speed and vice versa. So the speed of signal transmission through this space, not through the tracks, through the space, is much slower on the one on the left and quicker on the one on the right. And the problem is you may build that board one day like that. You may build the board the next day, and actually it's all moved over a bit. Or perhaps both traces are in both resin-rich or glass-rich. Who knows? You've no idea how they're going to fall. And that is a huge issue. So when you get down to this small scale, we're talking sort of 5 mils now as the scale here, you are very much in the range of the glass fabric structure interfering very much with your material.